going to happen if we do have more than one parameter that needs to be estimated? Well, then we can still use the maximum likelihood estimation, of course. We can still rely on our asymptotic multivariate normal distribution. But now the covariance matrix is, or now we have to work with the covariance matrix, right? And it will be obtained once again as the inverse of the Fisher information matrix. And that's the matrix with element R and S, say, given as follows. So now you're not going to work with the second order derivative with respect to theta, but you're going to take the derivative with respect to theta R and then the derivative with respect to theta S, or vice versa, right? And here you recognize again this equivalent form, or you're going to work with the product of the derivative with respect to theta R of the log density and the derivative with respect to theta S of the log density. Yeah. So these are the elements that I need to put in my Fisher information matrix then when I'm working with a parameter vector theta that has dimension larger than 1. So we're going to do an example now where we want to calibrate the log normal distribution to the losses from dataset B, and where we do not only want to have the maximum likelihood estimates for the unknown mu and sigma, but we also want to be able to write down a confidence interval for them, right? And we're going to do that analytically now. If I go with you to the computer labs next week, the week thereafter, then I'm going to show you how you can get these confidence intervals numerically from your optimization routines. Okay, let's do an example because I guess things are very obscure and abstract at this point. So what we're going to do is we're going to work with dataset B, 20 losses, and we're going to fit the log normal distribution to these losses in dataset B, right? So the log normal distribution, it makes sense because it's one of these typical severity distributions. It's not very, it's not heavy-tailed. It's a light-tailed distribution, but it has all its probability mass on the positive line. It's skewed to the right, etc. So it's an interesting distribution to potentially work with when dealing with severity data. So if I write down the likelihood, and if I assume these 20 losses in dataset B to be independent from each other, and to have the same distribution, so that means they have the same log normal distribution with the same mean mu and the same parameter sigma squared. It's not the mean, but I should say the same parameter mu and the same parameter sigma squared. Then my likelihood will look like this, right? So what you see over here, it's not the normal density. Huh? It looks similar, but it's the log normal density. So you can find that in your appendix, or you can derive that yourself with some of the properties we discussed earlier on. So this is my likelihood. If I switch to the log likelihood, that's what you see in the next step. Then I have the sum over j. I've got the logarithm of what I've got over here, right? So my goal is now I want to estimate both mu and sigma. And I do not only want to get point estimates for them, but also intervals. And I want to do that first in general expressions and then switch to the results that I have for dataset B, to the sample that I have over there, and then really fill in the numerics and get really an interval for the mu and the sigma. That's the idea. Now, of course, we're doing it here with pen and paper. In reality, you would do that numerically. You would put that up in R and get these results, right? I will show you how you can do that in the next sessions, but for now, it's good that you experience once how that would go in a manual way, let's say. Okay, so here we go. The first thing we're going to worry about is what are the derivatives? Yeah. The first order derivatives of the log likelihood with respect to mu and with respect to sigma. And I'm not going to do all the derivatives on the iPad. That would take us too much time. But if you look at getting the derivative, of the log likelihood with respect to mu. Well, the mu is only in this term. You see that over here. So you've got -1/2. You're going to multiply that with 2. You're going to have the ln of xj minus mu divided by sigma. And you're going to multiply it with 1/sigma. That's the, if you work it out with the chain rule, that's what you should get over here. So this is your first order derivative with respect to mu. You can do the same for the first order partial derivative of my log likelihood with respect to sigma, right? So with sigma, I've got a term over here. That's easy. That becomes -1/sigma. And I've got it here as well. So that's in fact sigma to the power -2, which I need to take the derivative of, right? Now, be careful if you look at this guy, it's going to give you as the derivative -1/sigma, but it's inside the sum. So I get it n times then, right? Because it's a constant that I'm going to sum n times together. So this is my first order partial derivative. Now, one of the things we could immediately start thinking about is what would this give? This set of two equations, what would that give us? In terms of finding the maximum likelihood estimates, right? So what I then would do is I would take this system of two equations, I would put them equal to 0, and I would solve for the unknown mu and the unknown sigma squared, right? So that's something you can check yourself. So make sure that you can use that to find an expression then for the maximum likelihood estimates of mu and sigma coming out of this system of two equations. What we're going to do is we're going to go a bit further at this point, and we're going to look at the second order derivatives. Yeah, and why do we do the second order derivatives? Because that's what we need if we want to put this Fisher information matrix together. If I want to put this Fisher information matrix together, I need the Hessian, I need the matrix with the second order derivatives. So here are the combinations that I wish to investigate. I'm going to take, again, the derivative with respect to mu of the derivative which I already had with respect to mu, right? I'm going to look at the second order partial derivative with respect to sigma, and I'm going to look at the mixed derivative. So take the derivative with respect to sigma of the derivative that I already had with respect to mu. So this gives me my second order partial derivatives, and I'll let you check those derivatives at home to get a bit of a feeling on that. And then we know what to do for the Fisher information matrix, for putting it together, because the theory told us that if we are looking at putting together our Fisher information matrix, in case there are multiple parameters that we need to estimate, what we then need to do is element Rs in the matrix, say, will be this expected value of this second order derivative. And then you need to pick the appropriate combination, right? So either 2 times mu, 2 times sigma, or then sigma and mu. You need to take the expected value and you need to put a minus in front, right? So there I'm going to use the relation that my Fisher information matrix is composed by minus expected value of the Hessian, the matrix with the second order derivatives. Now the question here is, what if you're going to take the expected value of those second order partial derivatives? Well, if you look at this guy, there is no x here involved, right? So taking the expected value is just taking the expected value of a constant, so that's easy. If you look at this guy, then there is an x involved, because you've got here the ln of xj, capital Xj, minus mu. So if you take the expected value of this guy, then you're going to get a 0 for this term, right? You're going to get a no, sorry, you're going to get sigma squared for this term, right? So what we're going to get here is the sum over j of the expected value of the ln of xj minus mu squared. And that reminds us of the expression for the variance of the logarithm of x. And I know that if x is following a log normal distribution, then the log of x is following a normal distribution with mean mu and with variance sigma squared. So what I will get over here is minus 3 times n times sigma squared divided by sigma to the power 4. So I'm left with minus 3 times n divided by sigma squared. So if I work that out with the first term, you'll get the expression here at the bottom. That's where it's coming from. It's because I'm taking the expected value of the logarithm of random variable xj minus mu squared, right? And there you recognize the variance of the logarithm of xj, and the variance of the logarithm xj is going to be here sigma squared. Okay. Now here things become simple, because if I look at the mixed partial derivatives, second order partial derivatives, then I'll get the expected value of the logarithm of xj minus mu, and that is 0, because the expected value of the logarithm of xj in the log normal distribution, that's equal to mu, so that drops here and I get a 0. So my Fisher information matrix will be a diagonal matrix where the off-diagonal elements are both equal to 0, right? And now I looked so far at the expected values of the second order derivatives of my likelihood. So the only thing I need to do is I need to put a minus in front to get the Fisher information matrix. I need to take the inverse if I then want to have the variance or the covariance matrix of my maximum likelihood estimators. So that's my last step here. If I change the sign, if I invert the matrix, and that's easy here because it's a diagonal matrix, then that gives me the variance covariance matrix of my MLEs. Yeah. And what I want to do then is I want to plug in the estimates for sigma in order to get actual numerical values here. The value for sigma and the value for the n, the number of observations that I'm working with, of course. Yeah. And that brings us back to what I said in the beginning. Yeah, how can I find for this log normal distribution the maximum likelihood estimates? Well, then I need to go back to my equations, the first order partial derivative with respect to mu of my log likelihood, put it equal to 0. And here I have the first order partial derivative with respect to sigma of my log likelihood. I put that equal to 0. And I'm going to solve this set of two equations in two unknowns. I'm going to solve that for mu and for sigma, right? So if you do that, you'll see that the estimate for mu is becoming the sample mean, but at the log scale, right? And that's very natural because if I take the log transform, then the ln of xj is going to follow a normal distribution with mean mu. So there also you would estimate the mu with the sample mean. And if I look at the sigma het squared, I'm going to do a similar reasoning. I know that the logarithm of xj is following a normal distribution with parameters mu and sigma squared. So there I would estimate the sample variance by looking here at an expression of this type. Yeah. So here you can now actually calculate this. You can plug in what is n. N is 20 for dataset B. What are the losses observed? I get them from dataset B. So for dataset B, I eventually find mu het is 6 and something. Sigma het squared is like this. If I plug in these values in our covariance matrix that we put together, then you get something like this. So that means if I take the standard deviation, if I want to know the standard deviation of mu hat, I need to take the square root of this diagonal element. If I want to have the standard deviation of the estimate sigma, of the estimator sigma hat, then I need to take the square root of the second diagonal element. So I can quantify that, and that ultimately leads me to some confidence intervals for the unknown mu and for the unknown sigma. So I take the point estimate, mu hat, I take the point estimate sigma hat, and I'm going to subtract or add 1.96, that's a quantile from the normal distribution, and I'm going to work with the standard deviation that I find for this particular maximum likelihood estimate. So you take the square root of the numbers that you encountered over here. Okay, so it's a complicated thing, but I wanted to show it at least for one specific example. So here we work with the log normal distribution. So we've got two unknown parameters, mu and sigma squared, and that allows us in this case to come up with point estimates for mu and sigma, and also with confidence intervals for these parameter values. Yeah. Any questions? So I'm going to ask you to work through the derivatives to check these steps, make sure that you got a bit of feeling for that, and then arrive up to the point here where we constructed these confidence intervals.